So, so we can find this voltage regulation by two methods. One is the direct method, and the direct method is simply this alternator. This is alternator, and this is the field winding, and this alternator is directly connected to the three-phase load. So we can directly connect to the three-phase load, and then we can find directly by using these voltages. We can find directly uh, voltage regulation. But in case of the indirect method, that is different. So so look at this indirect method of voltage regulation procedure. So in the indirect method, so we need to conduct the OC test first. We need to conduct the OC test first, and then we need to find the SC test. OC test nothing but open circuit test by using TPST, triple pole single thrown switch. By using this switch, we need to conduct this OC test, and then after OC test, we need to find the after OC test, we need to conduct the SC test. SC test means nothing but we need to close these switches, and we need to short circuit the R, Y, B terminals through a ammeter. Through a ammeter, we need to short circuit this test. So before finding this OC and SC test, and let us discuss how to find the armature resistance. Armature resistance. So, so the armature resistance, how to find the armature resistance RA means by using DC test analysis. So this is R, and this is Y, and this is B phases of alternator, and this is the neutral, and between the neutral and any one phase, not only R phase, in any one phase. So let us take this is R phase, and this is Y phase, and this is B phase, and for you need to apply the voltage here, DC voltage, that is DC voltage. And if you apply DC voltage, some current passes through the this R phase winding only, that is current IDC. And by using this VDC and IDC, nothing but you need to place a ammeter here so that you can recognize how much current is flowing, and we need to place a voltmeter here so we can find the voltage, whatever the voltage which is giving to this R phase. Then by using this two voltmeter and ammeter readings, we can find RA is equal to that is RDC. RDC resistance is equal to VDC by IDC. So by using this one, we can find the DC resistance of this R phase, but we need to find the AC resistance of armature resistance. Why AC resistance? Because this is alternator used to generate AC. So AC resistance is different, DC resistance is different. So according to the Faraday effect or skin effect, sorry, according to the skin effect, RAC is equal to 1.6 times of RDC. So for example, this wire is connected for DC, the resistance is 10 ohms. Same resistance if you connect for AC, nothing but same wire if you connect for AC, then the reactance is, resistance is 16 ohms. That is the difference. That is the difference between AC and DC resistance. So in this way, we can find this RDC, and if you multiply 1.6 for RDC, that will get RAC, nothing but armature resistance RA. So from we know the formula, E phase is equal to the root of V phase cos phi plus IARA whole square plus V phase sin phi plus IAXS whole square. IAXS whole square. This is root also available up to here, and here RA is available. RA is available here. RA. This RA we found by using the previous analysis, previous test or DC test, and we can find the DC resistance somewhat, that is VDC by IDC, and if you multiply 1.6 to the RDC, we will get a RAC value. So we got RA, and we need to find this excess. So we can find excess by using a OC and the SC test of synchronous impedance method. Now let us discuss how to conduct this OC and SC tests of an alternator. So OC test must be conducted up to rated voltage, up to generate the rated voltage. SC test must be conducted up to rated. This is rated voltage and this is rated current only. This rated current and rated voltage is available on nameplate. These rated voltages are available. So this is the schematic diagram. This is R, Y and B phases, and these three phases, any two phases are connected with a voltage, that is nothing but EOC. So the voltage available between these two phases is called line voltage, but we need to know we need a phase voltage. So phase voltage is equal to VL by root 3 we need to take. Then we can find this phase voltage because this is star connected one. Here field winding is available, F1 F2 terminals field winding is available. Field winding is connected to through a rheostat. You can see this rheostat, and you can vary the rheostat so that you can control the field current. And this is the DPST switch, that is nothing but to give the DC supply to the field winding. So this is the total schematic diagram. Here voltmeter is connected, and here ammeter is connected. This is for the short circuit test. Now let us discuss the OC test, open circuit test. So how to find the OC test? So OC test is conducted between voltage, nothing but open circuited voltage versus field current. So OC test is conducted between open circuited voltage, nothing but this voltage versus field current. This voltmeter here in the field ammeter is available. This is nothing but a field current. Between these two, whatever the test which you are conducting, such a test is called OC test. By using OC test, this is the let us say a table. This is a table. Here in one line, this is V phase or E phase. Or another one is field current. So like this. So now we need to keep this resistance to maximum position. If it is maximum position, field current is less. If the field current is less, induced EMF is less. So at the starting, EMF is very less. Let us take 20 volts. Field current is 0.2 amps. Now we need to increase you need to change the restart position, and nothing but we need to reduce the resistance position so that field current will be increases. Field current will be increases in the field winding. Field current increases in the field winding, so that induced EMF also increases. So that will be taken as like this. For example, increased field current is 0.4 amps and voltage is 40 volts. Again, the field current is increased by changing the restart position, that is 0.7. So for example, 50 volts. And again, if you change the restart position, and we will get we can increase the field current, that is 1 amp and 100 volts. Like that, we need to take more values. If you take more values, we will get smooth curve. We'll get a smooth curve. So you need to take this E phase on x-axis, field current on y-axis. So if you take these values on a graph sheet, we will get a curve like this. We will get a points like this. If we combine the points, that curve will be like this, exponentially increasing manner. So this is the curve we will get like this. So up to certain value, up to this point, voltage increases. Afterwards, voltage will be constant. This is called saturation point. This point is nothing but where the voltage does not increase. Such a point is called saturation point. So afterwards, the voltage will not be increases. only voltage will not be increased, that will be constant. So such a characteristics is known as OCC characteristics. Whatever the graph we will get from the OC test, such a characteristics are nothing but a OCC characteristics, nothing but open circuit test characteristics. It's a SC test. How to perform this SC test? So SC test also similar to the OC test, but here we need to eliminate this voltmeter. We need to neglect this. We need to remove this voltmeter, and we need to connect this R terminal, Y terminal, and B terminal, and we need to short circuit the R, Y, B three these three terminal through a ammeter. The ammeter is available here. This is ammeter. By using this ammeter, we need to connect the all the three phases in the short circuited manner. And the procedure will be, look at this one, this curve is drawn. So this OC test, SC test is drawn between ISC, short circuit current, this is ISC. So this is a short circuit current versus field current. So in the previous test, field current is available. In the present test, nothing but SC test also field current is available. The SC test is conducted between ISC versus field current. So let us take a box. So in this is ISC and another one is IF. Same procedure. This is also same procedure. Same procedure, nothing but we need to keep this rheostat at maximum position, and the maximum resistance will be available, and we need to decrease the resistance position so that we can decrease the field current. So for example, at starting, maximum resistance is there in the field winding, so that less field current, that is nothing but I'm taking as a 2 amps, and at the 2 amps the short circuit current is 20 amps, and you change the rheostat position, and you reduce the rheostat position, so that field current increases. That increased current I am taking as 5 amps, and the short circuit current is 100 amps. And again, if you change the resistance position, if you decrease the resistance position, this will be increases. Similarly, this is also increases. This is increases. Both will be increases. So if you draw a graph, nothing but by using this data, if you draw a graph that is purely linear, So I will explain later why this SC during the SC test, why the curve is linear. I will explain later, but now just remember the curve how it will be. And if you conduct the test in the laboratory also, you will get the same curve, linear curve. So this is the OC test. This is the OC test, and this is the SC test. So now by using the SCC characteristics, and this is the OCC characteristics, and this is the SCC characteristics. Look at this one, OCC characteristics done between. Look at this one. This is axis. This is E phase versus this is field current. E phase versus field current, that is one axis. This is OCC test. Similarly, another test, SC test is SCC, short circuit characteristics done between ISC. ISC is nothing but this is ISC. This blue curve is nothing but ISC, and this IF is common for both. IF is field current is common for both. Look at this one. OC test is nothing but E phase versus IF, and SC test is nothing but ISC versus IF. You can see variables are 1, 2, and 3 only available. That's why this is one E phase, this is the ISC, this is IF. This is the graph. So if you conduct the SC test, look at this one. One is field current, one is short circuit current. If you increase the field current gradually at a particular voltage, at a particular field current, we will get a at a particular field current, we will get a rated current, rated ISC current, rated ISC current. Nothing but if you increase the field current and if you rotate the machine, gradually armature current also increases. At a particular field current, you will get a rated current, rated rated armature current in the ISC, in the form of ISC. So by using OCC and SCC characteristics, this is a rated current. So we know the rated current of the machine by using the nameplate details, and by using nameplate details, we can find the rated current. So we need to measure the rated current in the ISC axis. This is ISC axis, and we need to measure the rated current here, and we need to extend this rated current up to this SCC characteristics. So from this one, you need to indicate a point, and you need to, this is nothing but ISC, and you need to extend this point up to OCC characteristics, and you need to indicate this point, and you need to extend this point up to EOC axis, open circuited voltage axis. This value is nothing but EOC. This voltage is nothing but, this height is nothing but a EOC voltage. EOC voltage. So to find the ZS, synchronous impedance, ZS is equal to EOC. EOC is nothing but this is the value. EOC is nothing but this is the height which we need to measure. We need to take into account EOC by ISC. ISC is nothing but this is nothing but ISC. This height is nothing but ISC. We need to measure from this ISC graph. So by using these values, we can find the ZS. So if you know the ZS, we already found this RA. RA also we know, but finally we found this XS by using ZS and RA values. So if you know this ZS XS, we can find this E phase easily. And if you know the E phase, we can find the voltage regulation. Voltage regulation is equal to E phase minus V phase by V phase into 100. In this way, we can find the voltage regulation by using the ZP, this is a EMF method or synchronous impedance method. This is the only method is having the pessimistic result. Pessimistic results, nothing but, for example, actual voltage regulation of the alternator is 5%. For example, I'm taking not 5%. The actual voltage regulation of alternator is I'm taking 10%. But in this method, the voltage regulation will be more than 10%. More than 10%. That's why this method is called pessimistic method. Pessimistic method of pessimistic method. So this is a good method compared to the MMF method. MMF method is nothing but an optimistic method, because the actual voltage regulation is 10%, alternator voltage regulation is 10%. Then by using MMF method, the voltage regulation we will get as less than 10%. So that is not a good one. That is not a good one. So that's why this is MMF method is nothing but optimistic method, and this is EMF method is nothing but a pessimistic method. So for example, if you got 99 marks, you can tell your friends and other your parents also. You can say like out of 99, you can say I got 90 marks. So that is good. So if you got 90 marks, if you say I got 99 marks to your parents or friends, that is not a good thing. So you are explaining nothing but decreasing. Less value is better than the more value, more rank value. Less value is nothing but less correct value is better than the more wrong values. That's why this EMF method will give the less. For example, voltage regulation of alternator is 10%. It will gives the more voltage regulation, nothing but 30% or 40% like that. So this is a good one, no problem. But in the MMF method, if the voltage regulation of alternator is 10%, that will give less than 10%, nothing but 5%, 4%, 3% like that. That's why OCC characteristics, SCC characteristics, and by using these data, we can find the voltage regulation by using the EMF method. This is also called pessimistic method. This is also called pessimistic method. So, what are the advantages of this method? So, the main advantage of this method is the synchronous impedance for any load condition can be calculated. This is the most important one. So with any load, synchronous impedance can be calculated because this is OCC, this is SCC. At this load, at every load, we can find the synchronous impedance. That is the one of the important advantage. And the regulation of the alternator at any load condition and at power factor can be determined. So at any load condition, at any power factor can be determined by using these tests. This is another important one. Next one is actual load need not be connected to the alternator. So no need to connect the load, which means no need to connect the load. So this method is can be used for very high capacity of alternator. So this is used for very high capacity of alternators. So limitations of this method, synchronous impedance method. So the main limitation of this method is this method gives a large values of synchronous reactance. So as I told in the previous, pessimistic means large values of synchronous reactance mean more voltage regulation, So and because of this high reactance, large value of the reactance, this leads to high values of percentage reactant than the actual value. For example, actual value is 10%, but in this method it gives high values. High values nothing but 12%, 14%, like that it will give. Hence, that's why this method is called pessimistic method. That's why I explained in the previously how it is pessimistic. So by using this OCSC and SCC characteristics, this is the OCC characteristics and this is SCC characteristics. And if you draw OCC and SCC in only one graph, that will be like this. This is a ISC axis and this is the EOC axis, and this is field axis. And so by using SCC test, we can find the rated current. We can find the rated current as it mentioned in the nameplate, So we need to take that. We need to measure that rated current, and we need to indicate or we need to recognize that rated current in the ISC axis. For example, this is 10, 20, 30, 40. This is 100. For example, rated current is 100 amps. This is 20, 30, 40, 50. This is 100. We need to recognize this 100 point on the ISC axis, and you need to extend that ISC up to SCC characteristics, and indicate that point, indicate some point. So this is, and you need to extend this point up to OCC characteristics. And we need to measure this is EOC voltage. This is EOC voltage. How much? To measure this value and to recognize this value, we need to extend this value to up to EOC axis, so that we can estimate this EOC. So in this way, we can find EOC and ISC, and if you ZS is equal to EOC by ISC. So EOC from this value and ISC from this here 100. This is the rated value. So in this way, we can find the ZS. This is ZS. And ZS, we got the ZS value, and previously we got the RA, and now XS is equal to under root of ZS square minus RA square. So in this way we can find XS. So this is the formula: E phase is equal to V phase plus V phase, this is already available in the problem. Nothing but in the, if you solve a problem, you can understand they will give E phase, V phase, and power factor and current. We already know the RA and the voltage, and this is from the power factor. Plus or minus for the lagging or leading. IA we know. Excess. This excess from this data. Excess from this data. So that we found this E phase, and then our voltage regulation is E phase minus V phase by V phase into 100. So this E phase from this data, and a V phase we already know this is the value, and this is V also from this value, so that we can find the voltage regulation. This way we can find the voltage regulation by using the uh, synchronous impedance method. So let us discuss the advantages. What are the advantages? First one is the advantage of this synchronous impedance method is uh, at any load condition we can calculate the synchronous impedance. This is another advantage, one main advantage. So at any load we can find the find the synchronous impedance, which means at any load condition we can find the voltage regulation. So at any load condition, at any, and power factor also, at any load condition and at any power factor also we can find the synchronous impedance. So here actual load need not be connected, nothing but actually no need to connect the load. And also this method is used for high capacity alternator. So the limitations are, so the main limitation is this method gives large values of synchronous reactance. So excess is more, which means actually if the alternator is having excess is equal to 20 ohms, but in this method excess will be 25, 26, 28, more than 20 ohms. That is one of the limitation and of this method. And because of this one, it will this will give some more voltage regulation, because E phase is equal to under root of will have V sin phi plus IA excess. So plus is available, so that if excess increases, the E phase also increases, so that regulation will be more, percentage regulation will be increases. So that is another limitation. And because of this one, this method is called pessimistic method. So this method is called pessimistic method. Because of this large values of synchronous impedance, more voltage regulation will be there. Because of this more voltage regulation, this method is called pessimistic method. Pessimistic method means more than the actual values. For example, voltage regulation of the alternator is 10% actual voltage regulation. But by using this method, we will get more than 10%, nothing but 12%.